Diaphragm seals, isolating instruments for accurate, maintenance-free measurement. Purpose and application, isolation without compromise. Diaphragm seals serve as a protective barrier between the process fluid and the measuring instrument, eliminating the need for impulse lines in surfaces prone to plugging, corrosion, high viscosity, or extreme fouling. By filling the space between the diaphragm and the sensor with a stable, inert fluid, pressure can be accurately transmitted while completely isolating the instrument from direct fluid contact. These seals are essential in applications involving waxy hydrocarbons, aggressive acids, or particulate-laden flows, where traditional impulse lines would rapidly clog or degrade. They are also used where maintenance access is limited or where zero dead volume and hygienic conditions are required, such as in food-grade or pharmaceutical processes. Mechanical integration, matching process geometry and ensuring clean flow. For new installations, the process nozzle must be specified to match the flange size of the diaphragm seal to eliminate the need for reducers. Where reducers are necessary, such as retrofitting onto smaller legacy nozzles, they must be eccentric and installed such that the bottom of the reducer aligns flush with the isolation valve seat. This prevents pockets where sediment or solids could accumulate, maintaining full flushability and reducing the risk of fouling. The diaphragm itself must be installed with precision to ensure a seamless, uninterrupted face to the process. Flush-mounted configurations are essential for clean-in-place CIP or drainable systems, while extended diaphragm styles are better suited for tanks or vessels with recessed nozzles. Calibration design, adapting to plug-free installations. In systems where diaphragm seals are used to prevent plugging, equalizing lines are typically avoided as they present the same clogging risks as traditional impulse tubing. Instead, these systems rely on vent ports, flushing rings, or purge connections for calibration and maintenance activities. In such configurations, zero calibration is conducted at atmospheric pressure using known fluid levels or by adjusting the transmitter based on known head values. Vent valves be strategically located to allow safe pressure release and displacement of trapped air or seal fluid during initial filling or servicing. For less severe services where fouling is not a concern, equalizing lines may be introduced to allow in situ zero and span calibration at full process pressure. These systems offer enhanced accuracy and allow for re-zeroing without removal, particularly valuable in high-pressure or critical level applications. Flushing and maintenance provisions. Keeping the diaphragm clean. Flushing rings or spacer assemblies may be installed between the diaphragm and isolation valve to provide ports for chemical cleaning, solvent flushing, or purge gas injection. Alternatively, diaphragm seals may be paired with orifice flanges when welded valve bodies are used, ensuring secure sealing and access for maintenance. These features must be selected based on process fluid behavior, whether it is sticky, polymerizing, or subject to sedimentation, and on the need for frequent servicing. All configurations must allow access without requiring removal of the seal from the process line, preserving containment and reducing downtime. System coordination. Seamless interface between disciplines. The successful application of diaphragm seals depends on coordinated design across mechanical and instrument engineering teams. Seal installation must respect flange ratings, bolt torque tolerances, material compatibility, and expansion dynamics of the fill fluid. All components, diaphragm, fill fluid, housing, and connections, must be compatible with expected process temperatures, pressures, and exposure durations. Thermal expansion of fill fluid must be accounted for during calibration to avoid drift or rupture, especially in applications where the diaphragm is exposed to large ambient or process temperature fluctuations. Trace heating and insulation may be required to maintain fluid stability in colder environments. Conclusion: sealed precision for challenging process environments. Diaphragm seals offer an elegant solution to some of the harshest measurement challenges. By isolating instruments from direct contact with problematic fluids, they ensure long-term stability, eliminate blockages, and reduce maintenance frequency. Their correct application, from flange selection to calibration strategy, enables reliable, high-integrity measurement where conventional impulse lines would fail. Each installation must be custom-tailored to fluid behavior, access requirements, and operational conditions to realize the full benefit of this robust measurement approach. External purging, active flow assurance for clean, unobstructed signal transmission. Purpose and application, clearing the path for accurate measurement. External purging is employed when passive strategies like sloping impulse lines or diaphragm seals are insufficient to prevent plugging, condensation, or vaporization in the measurement path. It involves continuously injecting a clean, inert purge fluid, typically a gas or low viscosity liquid, into the impulse line to prevent process fluid ingress, clear obstructions, and maintain a stable measurement interface. While external purging increases system complexity and requires regular oversight, it is often the only viable solution for processes involving crystallizing fluids, solids-laden streams, rapid polymerization, or unstable phase conditions. Properly applied, it provides a consistent medium through which pressure or differential pressure can be transmitted without contamination or lag. Design considerations: controlled, constant flow under all conditions. The purge system must ensure a low but steady flow of purge fluid under all operating scenarios. The purge supply must be at a pressure consistently higher than the process pressure, but below the maximum design pressure of the equipment, to avoid overpressurization and ensure one-way flow. The purge fluid must be chemically inert and non-reactive with the process, single-phase and free of entrained solids, non-corrosive to tubing and fittings, compatible with downstream equipment and not interfere with process chemistry. Injection points must be located close to the process connection to minimize pressure loss or measurement distortion caused by flow-induced differential. In low-pressure or vacuum applications, this becomes especially important as even minor purge flow can create significant offsets if introduced too far from the source. Purge assembly, built-in safety and operational control. A complete purge system must include filtration to prevent solids from entering the impulse line, soft-seated check valves to block reverse flow, flow restrictors or orifice nipples to control purge rate, vent valves equipped with tamper-resistant mechanisms, isolation valves for maintenance and operational control. Purge flow can be maintained using either calibrated orifice fittings or constant flow controllers. In gas and steam applications, critical flow across a restriction orifice ensures a stable flow rate regardless of back pressure, simplifying system tuning. Structural integration, seamless with instrument and process hardware. For vessel-mounted applications, purge pipes and isolation valves must be integrated into the equipment design. Side-mounted connections are preferred, but top-mounted options can be used where geometry or process layout demands. Mechanical engineering is responsible for the design and installation of the purge piping up to the instrument tapping, while instrument engineering specifies purge assembly components and flow control elements. Instruments subject to purge gas injection must be located above the maximum liquid level, with impulse lines sloped downward toward the process. This ensures that the purge gas displaces any liquid formation and does not create pockets or traps that could lead to inaccurate pressure transmission. Limitations and maintenance demands. Why purging is a last resort. Despite its effectiveness, external purging is maintenance intensive and should only be used when simpler solutions such as heating, seal fluids, or self-purging geometry are impractical. Over time, purge systems are prone to issues such as flow rate drift, check valve failure, or inadvertent supply interruption, all of which can cause measurement errors or process upsets. To mitigate these risks, purge systems should be installed with pressure indicators or flow monitors to provide early warning of failure. Regular inspection and cleaning of filters and valves are required to maintain purge performance. Conclusion: active clearing for persistent measurement challenges. External purging is a dynamic solution for hostile or unstable measurement environments. It creates a protective flow barrier that shields the instrument from clogging, chemical attack, and physical degradation. When designed with precision and maintained with discipline, a purge system transforms otherwise unmeasurable processes into manageable, monitored flows. However, due to its operational demands, it should be used only after evaluating and exhausting simpler passive alternatives. Self-purging, passive evacuation for stable, maintenance-free signal transmission. Principle and application, harnessing process behavior for natural line clearing. Self-purging relies on the natural phase behavior of the process fluid, typically its tendency to vaporize at ambient conditions, to prevent the accumulation of liquid or solids in impulse lines. By using heat influx from the environment or auxiliary heating to drive evaporation or prevent condensation, the impulse line remains clear without active intervention. This strategy is particularly valuable in cryogenic or low-temperature services where process fluids vaporize rapidly when exposed to warmer surroundings. It is also used in gas services where condensate formation is minimal and pressure differentials are sensitive to fluid presence in the impulse path. Self-purging eliminates the need for flushing, draining, or external purge systems, reducing both operational cost and system complexity. Impulse line geometry, enabling gravity-assisted drainage. For self-purging to be effective, the physical routing of impulse lines is critical. From side-mounted process tappings, lines must descend vertically from the instrument and then slope gently downward toward the process at a consistent gradient, typically 1/5. This geometry ensures that any vaporizing fluid flows back to the process by gravity and that residual liquid is cleared by the expanding vapor. Vertical drops from the instrument to the sloped section should be minimized to avoid forming static liquid columns that might interfere with accurate pressure transmission. Tubing must be routed with care to prevent traps, dead legs, or flat sections that could accumulate condensate or non-condensable gases. Thermal management, balancing heat retention and controlled evaporation. The effectiveness of self-purging hinges on maintaining appropriate thermal gradients to prevent unwanted heat gain at the process interface, which could increase fluid loss or alter process conditions. The first section of tubing near the tapping must be insulated. A 300 millimeter segment is typically sufficient to reduce conduction into the process. Beyond this, thermal treatment depends on the fluid composition. For fluids where all components will vaporize under worst-case conditions, a bare, non-insulated tubing section of at least 300 millimeters should be exposed to ambient air to assist evaporation. For fluids containing heavy ends or non-volatile fractions, this section must be heated and insulated to ensure complete vaporization and prevent residue buildup. All insulation or heating elements must be installed in a way that does not interfere with access, identification, or thermal expansion of the tubing. Process limitations. Best fit for select services. Self-purging is ideal for low-pressure gas systems, cryogenic services, and clean vapors where small amounts of condensate may form and naturally return to the process. However, it is not suitable for fluids with high pour points, solids, waxes, or reactive components that leave behind residue upon evaporation. In such services, partial evaporation can create scale, coking, or measurement noise, negating the benefit of passive purging. In these cases, active purging or alternative measurement technologies should be considered. Direct mounting constraints, thermal exposure and stress risks. Direct mounted instruments are typically not suited for self-purging applications. The proximity of the sensor to the process fluid exposes the instrument to extreme cold or large temperature swings, potentially exceeding the limits of sensor fill fluids or electronics. Additionally, the compact structure of direct mount systems does not allow sufficient distance for thermal control, phase separation, or safe vapor dissipation. In contrast, remote-mounted configurations provide the spatial flexibility needed to implement self-purging geometries while protecting sensitive components from temperature-induced damage. Conclusion: passive performance through design intelligence. Self-purging offers a low-maintenance, energy-efficient solution for managing impulse line cleanliness in suitable process environments. When implemented with correct tubing slope, thermal control, and elevation planning, it enables stable and reliable pressure transmission without manual intervention. Though limited to specific fluid behaviors and process conditions, self-purging represents a powerful tool in the instrumentation engineer's toolkit, delivering measurement reliability through thoughtful exploitation of natural fluid dynamics.